Hi guys, this week's lecture is all about evaluating classifiers. So we're going to talk about two things. First off, we're going to look at evaluating classifiers and we'll look at a couple of different measures that are useful for doing that. And then we're going to talk about something quite interesting. It's called the bias-variance tradeoff. And this is a way to understand the kinds of errors associated with classifiers and how to choose the best classifier. So first off, looking at evaluating classifiers. Well, the basis for evaluating all classifiers is using something called a confusion matrix. And usually we end up using the measures we end up devising measures that are based on the values that are in the confusion matrix. So let's look at the basic confusion matrix first off. Hopefully you won't find it too confusing. Now, here's our confusion matrix. So you can see that we've got four squares, and you find this kind of thing if you have a classification problem with just two cases. So there's two cases, a positive case and a negative case. So along the rows, we've got the predictions. So the first row is all of the predictions that are positive. So all the positive predictions by the classifier. And on the second row, that has numbers that are associated with negative predictions. So these are all the predictions that the negative predictions that the classifier makes. So that's along the rows. Along the columns, we've got what the actual data has. So we're usually comparing the predictions on some test set. So the columns are talking about we'll have numbers that are associated with the actual number of positive data points in the test set and the actual number of negative data points in the test set. So in the top left corner we've got this cell called TP. Now that's going to have a number in it, and that number is the number of data points in the set being tested, so the test set, that were actually positive in the test set and were predicted as positive in the test set. So they're called true positives. So that's the number of data points in your test set that were actually positive and were predicted as positive. So they're the ones where the classifier has made the right classification. In the bottom right-hand corner, where it says TN, they're true negatives. So this is the number of data points in your test set that were actually negative and were predicted by the classifier as negative. So again, these are ones where the classifier has made the right choice. Now, in the first row, in the second column, so we've got a thing called FP. FP means false positives. So this is the number of data points in our test set that were actually negative, but were predicted by the classifier as positive. So this is false positives. They were falsely predicted as positive. These are ones that are obviously errors. And the number here is it's called the type 1 error. And in the opposite corner, where it says FN, they're false negatives. So these are the number of data points in our test set that were actually positive, but were predicted by the classifier as negative. So they were falsely predicted as negative. So this is usually called the type 2 error. And when we're trying to build a classification, we might have a trade-off between the type 1 error, the type 2 error. Sometimes it's better to make more classifications one way or the other. So this is just a summary of that slide. So T is true, F is false, N is negative, P is positive. So TP is the number of correct predictions that an instance is negative, TN, true negatives. FP, false positives, is the number of incorrect predictions that it's positive. FN is the number of incorrect predictions that it was negative. And TP is the number of correct predictions that an instance is positive. And just to give you a concrete example, here's what you would see, the kind of thing that you would see in a confusion matrix. So we can see that we have in our set 200 plus 100 plus 25 plus 5 is 325 data points. And there were 200 that were actually positive that were predicted as positive, and 100 that were negative that were predicted as negative. And then there were 5 that were actually negative but were predicted as positive, and 25 that were actually positive that were predicted as negative. So you can see what the confusion matrix would look like in an example test set. So we don't usually use the confusion matrix as it is, although it gives you a lot of information about what's happening. Usually you can see whether the classifier has predicted everything as positive, in which case there's nothing in the actual the predicted negatives are all 0, and that gives you some information about what the classifier is doing. But usually we have measures that are based on the numbers in here. So here's just 4 measures that are commonly used. The first one you would know about. It's called accuracy. So this is just the number of true positives and true negatives, so the correct predictions, divided by the number of all predictions, so just all of the squares added together. So that's accuracy. We have error rate, which is the opposite, so that's the number of false positives and false negatives divided by all of the predictions. And then we've got something called true positive rate, which is the proportion of true positives to all the positives. So the ones that were predicted as positive divided by all the positives. And we've got false positive rate, which is the number of false positives to negatives. And this true positive rate and false positive rate we'll see again in a few minutes. It's quite useful. So we can often change classifiers to bias them towards making type 1 versus type 2 errors. And it's a common trick that you use when you have an unbalanced data set. So something like fraud detection or those kinds of problems. So accuracy and error rate seem to be really useful measures, but they don't work very well in practice. The problem is that they're biased if there's different numbers of items in each class. So when the classes are balanced, when you have roughly the same number of positives and negatives, then accuracy and error rate work really well. But if they're unbalanced, if you have a lot more positives to negatives in your data set, or lots of negatives to positives, then the accuracy and the error rate are not very descriptive. So let's look at an example. So here we've got a data set of 100 customers, and 10 of them bought an iPad, and 90 of them didn't buy an iPad. So it's quite unbalanced. So if we build a classifier that always predicts that a customer will not buy an iPad, then its accuracy is going to be 90%. But in reality, it hasn't solved the problem at all. So it's actually a really poor classifier, but accuracy 90% sounds really good. So the accuracy it doesn't really make sense very well when you have unbalanced classes like this. It's much better to use true positive rate or true negative rate instead. And you can see what we have down there for those. So rather than using accuracy and error rate, people tend to use other kinds of measures. So the other common ones that you'll see are precision and recall, and sensitivity and specificity. So precision is measuring how accurate the positive predictions are. So it's the ratio of true positives to all the predicted positives. Recall is the same as a true positive rate, and that's the number of true positives. It measures how many of the actual positives the model can find. So how many of the positives are true positives. So if it's 1, then that means the recall is perfect. We've also got sensitivity and specificity. Sensitivity is the same as true positive rate or recall, and it's how sensitive the model is. And then specificity is the same as the true negative rate, and that's just how many of the actual negatives the model found. Sensitivity and specificity you tend to see in scientific kind of applications. So if you do anything in medicine or biology, they always talk about sensitivity and specificity of models. Precision and recall come from information recall or document recall kinds of tasks, or often image processing, you get precision and recall. So they're just sort of alternate measures that you're going to come across. Another measure that we use is based on something called an ROC curve or an ROC graph. So OC stands for operating characteristic curve. ROC stands for receiver operating characteristic curve. So it was originally used in the communications area to look at false alarm rates. It's also used in information retrieval. So what the ROC graph does is that it's a plot with the false positive rate on the x-axis and the true positive rate on the y-axis. And they're the false positive rate and the true positive rate that we saw a couple of slides back. So this is a sort of what it looks like. So the x-axis is the false positive rate. So that should be 0, 0.1, 0.2, blah, 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 all the way up to 1. And so that's the false positive rate. And the true positive rate is along the y-axis. So a classifier will be 1 point on that curve, in that graph. So on the top left, at the point 0, 1, that's the perfect classifier. So the false positive rate is 0, so it's not getting any false positives, but it's getting all true positives. So it classifies all positive and negative classes correctly. On the bottom left, we've got the point 0, 0. So that's a classifier that predicts all the classes to be negative. So the false positive rate's 0, but the true positive rate's 0 as well. And the point at the top right, 1, 1, that's the classifier that predicts all cases to be positive. So again, it has a true positive rate, which is fantastic, but the false positive rate's really poor. And the point at the lower right-hand side, the one that you hope you'll never get, is the point 1, 0. So that's a classifier that is incorrect on every single classification. So the false positive rate is 1 and the true positive rate is 0. So generally, the classifiers are going to be in that. The further they are towards that top left-hand side, the better the classifier. Now it turns out that we don't usually see our classifiers as points, and that's because most of the classifiers we look at are parametric classifiers. So they have parameters that can be modified. And what we normally find is that our classifier, the classifiers you'd use in KNIME or in RATTLE or RAR, will be curves along this on this ROC graph. And you can see two examples there. They sort of bow out towards the 0, 1 point. The further that the curve bows out towards that top left-hand side, the better. If you have a curve that goes straight up and straight across, then that's perfect. Now, the line that goes from the bottom left-hand corner to the top right, that straight line, that's essentially random guessing. So you want curves that bow out from that more. So, as I said before, often classifiers have parameters that can be used to adjust the true positive at the cost of increasing the false positive. So non-parametric classifiers are points, parametric classifiers are lines. So some features of ROC curves. The ROC curve is independent of the class distribution or the error costs, so they don't have that problem of bias when you have different numbers of data points in each of the classes. Unfortunately, it only works with binary classifications, so you can't really do an ROC curve for non-binary. So for the iris dataset, for example, you can't really do an ROC curve. You'd need to do one class versus the rest. So the ROC curve, it's an easy way to understand how the classifier works. It encapsulates all the information that's in the confusion matrix, and it's a really good way to compare a whole lot of curves. So you can put a whole lot of different classifiers all on the same ROC graph, and it's usually really obvious which one is bowed out as much to the left as possible. So people often use another measure once they've got their ROC curve. So if you work out the area under the ROC curve, that's going to be a value between 0 and 1. and it's often called AUC, the area under the ROC curve. So the higher that number is, the better the classifier. So the AUC is the probability that the classifier ranks a randomly chosen positive instance higher than a randomly chosen negative instance. There's been some recent research, though, that suggests that there might be some issues with just using that AUC to model the comparison between different classifiers. Although in practice, many people do that, and certainly I would use it. So drawing an ROC curve, generally you wouldn't draw one yourself, you would have some software to do it. So any of the classifiers that can produce some kind of score or a probability of membership to the predicted class, then you can draw that curve rather than just having a single point. And I'm not going to go through all the details of how it works, but what happens is you get the test instances and you rank them by the probability of belonging to the positive class, and then starting from that lower left point, every time you have a true positive you draw a line up, and every time you have a false positive you draw a line right towards the right, and eventually you get to the top right hand corner. And when you do that, these are the kinds of diagrams that we generate with either Rattle or Nine. And that's going to show you how you would do that in Rattle and Nine. First off, Rattle. So in Rattle, there's an Evaluate tab, and there's a few options here that are useful. That error matrix that you can see on the left, if you tick that one, then you'll get a confusion matrix. If you tick the .ROC, the ROC dot, then you'll get an ROC curve. And the last one that's also quite useful is score. And if you do that one, then you can score some data points, your test data points, to see what value they would get. Let's look at how we would use KNIME, though, to do an ROC curve. So here we have a whole lot of nodes connected together in KNIME. So what this is doing is, on the left-hand side we have a CSV reader, and it's going to read the iris.csv file. So you already know how to do that. Next thing we're going to do is binarize the class variable. The reason I'm doing this is because, remember, the ROC curve can only deal with binary classifications. So what I'm going to do is create, I'm going to binarize the species attribute into 3 columns, one for Setosa, one for versicolor, and one for virginica. And just to give you an idea of how we're going to do it, this is the configuration dialog for the one-to-many node, which is the one that can binarize the class. So you can see I'm just doing it for species. Next is number to string. So because it binarizes it, it makes a new integer attribute for Setosa, virginica, and versicolor. So we need to convert those numeric attributes to string attributes, or to categorical attributes. The next thing we want to do is filter out all of the columns that we're not interested in. So we use a column filter node to do that. And this is what I have here. So I've filtered out, I'm excluding the species, because that was the original class attribute, we don't need that anymore. And I've just chosen versicolor to be the one that I'm going to make a prediction for, so I've excluded Setosa and virginica. You need to exclude species, because otherwise it will use species to predict versicolor, and you'll build a really good classifier, because you're using the answer to make the prediction. Okay, next thing we're going to do is, you know how to do the partitioning, you know how to do the decision tree learner. So the next thing we're going to do is you need to make a little bit of a change in the decision tree predictor so that you can build a ROC curve. So the only thing that's a bit funny is here. So you'll see in the configuration menu, we're still going to use prediction versicolor as the attribute name for the prediction, but you need to tick this next bit. And it says append columns with normalized class distribution. This just means that it adds a new column for the probability of versicolor being 0, and the probability for versicolor, the class attribute, being 1. We need to do that because remember what we were saying before, when we want to draw the ROC curve, we need to have the probability that we need to order the test points in the probability that they're predicted as the class. So you just need to add that column, otherwise it won't work. Finally, we've got the ROC curve. So in this config, there's a couple of things to get right. The first one is the class column. So you need to make sure that the class column is the actual is the attribute that contains the actual class value in it. Positive class value, we want to set that to 1 because that just means a positive prediction. It has the value 1, the class value 1. And this last bit, we need to include the columns that have positive class probabilities. And for that, we want to get rid of all of the attributes except for probability that versicolor is 1. I'll keep that one. So when we do that, and then we look at the resulting picture, for the decision tree, you get this. So you can see this is our ROC curve. You can see that there's the diagonal, that's random guessing, and you can see that the decision tree has actually done a pretty good job. It's bowing out quite a long way towards that top left-hand corner. At the bottom on the right-hand side, you'll see a thing that says probability of versicolor equals 1, 0.90222. That's our area under the curve. It's not very clear from that, but that's our area under the curve. So this is how you can do ROC curves in KNIME and in Rattle. Next, we're going to look at this thing called the bias-variance decomposition. So this is a formal method for understanding prediction error of a model. And what it says is that for the test error, the error that we find in our test set for a data point, can be divided into 3 components. The bias, the variance, and the noise. So bias is all about the average distance between the target and what the model predicts. So it's talking about how well can the model do for any training set we were likely to choose. Intrinsically, how good is the model at solving the problem? We're going to go into this in a lot more detail in a minute. Next one is variance. So variance is the deviation between the predicted value and the average predicted value. So this is measuring the sensitivity of the classifier or the prediction model to a particular training set. So variance is high when your model is very sensitive to the specific training set that you happen to get. And the last one, noise, is just the change in the target value or the noise inherent in the problem that we can't really get around. So with bias, the classifier has to make some kind of informed guess in the areas that aren't covered by the training data. And this is a design choice. So and it's to do with the complexity of the model. So if we have a decision tree with lots of nodes, so less pruning, then it's making quite strong assumptions about the decision, about the problem it's trying to solve. And we would say that the stronger the assumptions it makes, the more biased it is. So essentially, the simpler the model, the more biased it is. If it's a really simple model, it simply can't model a complicated thing, a complicated problem. So bias is intrinsically talking about how complex the model is. So the simpler the model, the more biased. Variance is about the variability in the training data. So classifier error is affected by variability in the training data because when you use different training sets, you end up getting different decision boundaries. So high variance in a model means that if you choose different training sets, you get a big difference in the result, in the outcome. So it means it's more sensitive to particular training sets. So generally, if models have less parameters, if they're simpler, then they have low variance. If models have lots of parameters, then they have high variance because they fit the noise in a particular training set. And the last component is noise, and this is just the inherent noisiness of the class labeling or the output. And these errors are unavoidable even when you know the correct decision boundary, the correct line between the positive and negative cases. You can't really get away from the noise. So we can summarize what it's about on this slide. So this is showing the prediction error for a training sample and the test sample. So the error you would get on the training set and the error you would get on the test set. The error on the training set is the blue line. The error on the test set is the red line. And so error is on the y-axis, and along the x-axis is model complexity. So if you have a very simple model, low complexity, then you have high bias and low variance. So high bias because the model isn't very complex, so it's going to have a high error component because it simply can't model the real world, the problem very well. If you use a linear model, it can't understand a non-linear phenomenon. So the error is higher. It has low variance because the model's really simple. It's silly. It doesn't, or stupid. It doesn't. You can choose lots of different training sets, and it's not really going to change, or versions of the training set, and it's not really going to move very much. On the other side, we have models with very high complexity. So these are models that are very flexible, that can understand subtleties in the data. So these models have low bias, so they can understand the complexity of the problem being solved, but they also have high variance. If you choose a different training set, you might get quite a different model. You might get a different answer. So they're quite sensitive to the specific training set that you're getting. So they have high variance but low bias. And what we have to do is choose a model complexity that is in between. We don't want too low model complexity because the error has a high component of bias, and we don't want to choose a really, really overly complex model because then it'll have an error component that has high variance. So we want to choose one that has a low enough bias but also a low enough variance. So we can't do that with just the training sample, because what happens is that we end up getting a more and more complex model, and it fits the noise in the training sample, and so we'll get a low error. But if we were to choose another data set, so another training set, for example the test set, it's not going to have as good an error because of the high variance. So generally what we do is we train our model and we choose the model complexity where the error starts to increase on the test sample, because that will be an indication that the variance is starting to climb. Okay, let's look at bias, variance and noise in a little bit more detail. We're going to look at a regression example first off. So here we've got a y, so the value we're trying to, so we're modeling some relationship. So our assumption is that that using some function of x, our inputs, we can model our y, our output. And there's the epsilon is an error term, which is has zero mean. So we're assuming that using our machine learning, we can find a function. We have a function f that takes our inputs x, and we can use that to find our output y, but there's an error associated with it. So this is what our machine learning algorithm is doing. So the f hat is the prediction the function that we're predicting. So f is the real function in the outside world. F hat is the prediction that we're trying to make. So using the input x, and using our prediction of, or our approximation of the function f, we get our predicted y, our predicted outcome. And obviously, we're going to try and find an f that gives a y hat that's as close to y for a particular x. So how are we going to measure this accuracy of our classifier, so of our f hat? Well, we can do it by measuring the difference between the y hat that we found versus the y that we know we should have. And we can do it using this. So this is showing y minus y hat is the difference between what we want and what we predict. We're squaring it to get rid of the negatives, and e just means the expected value, so the averaged over all of our data. It turns out that the expected squared difference in y values, we can call it our error, depends on two components. So because our y is f of x plus the epsilon, we can replace the y with f of x plus epsilon and then subtract f hat. And it turns out that with a little bit of algebra, we can decompose that into two components. The first part, f of x minus f of hat x, so the difference in predictions squared, that's called reducible error, because this is the error that we can reduce and by choosing a better f hat. If we have a really good f hat that exactly mirrors f, then that reducible error is going to become 0. There's another component to the error though as well, and that's the variance of the epsilon, and this is the irreducible error. It doesn't matter how good an f hat we find, we can't reduce that amount of error. This shows that the error of our classifier is bounded by that irreducible error. So we're interested in trying to reduce the reducible error because that's what we can work on. So let's look at the regression case in a bit more detail. So one measure that's often used is MSE, which is the mean squared error. So mean squared error is simply so we have n data points in our set that we're looking at. So we're taking, yi is the actual output for the ith data point in our set. So f hat and xi is the inputs for our ith data point. So f hat xi is what our algorithm produces. So yi minus that is the error for that one pattern. We can square it, add this up for all of our data points, and then divide by n, so it's the mean squared error. So we're interested in trying to minimize this mean squared error. We don't want to minimize it just for our training data, because then because it doesn't work very well to use. We actually want to find the f hat that has the minimum mean squared error for data that we would see in the outside world. We don't want the classifier that produces the minimum mean squared error for the data that's in our training set, because we may have over-trained our model. And we can't use the training set as a proxy for what we'd see in a test set, in the real world, so we need to use a test set. So this picture that's below is what we saw before. So we're choosing a complexity, so we're choosing a f hat that that minimizes the test mean squared error. And that green line is the minimum possible test mean squared error over all of the methods that we can find. And that's the variance of our epsilon, our error term. So we can't find, that's the best we could possibly do. So it turns out that in the regression case, when we use this mean squared error, we can divide our expected expected test mean square error into several components. And I'm not going to go through all the maths for all this, but this is sort of how it falls out. So what we've got on our left is the expected test mean squared error, so the mean squared error in the outside world, and that's the average mean squared error if we repeatedly estimate f using lots of different training sets and then testing it at x0. So we're only interested in the test MSE at point x0. So expected test MSE is the average mean squared error, so that's what that expectation is. If we repeatedly estimate f using lots of different training sets, but test them just at that x0 value. So that's our expected test mean squared error. Next bit is our variance. So this is the amount that f hat, or our predicted f, would change if we estimate it using different training sets. That's the variance term of our error. The next bit is the bias. So the bias squared, this is the error that's introduced by trying to approximate the real function, the function in the real world, using some simpler function. So for example, if the real relationship between x and y in the real world is some non-linear function of x, and we're trying to model it with just a linear function, then there'll be a difference there, and that difference is the bias. And the last part is the irreducible error. So this is just the error inherent in the problem. That's where that green line was before. Now, because variance is inherently non-negative, and bias squared has to be non-negative, then the lowest that they could possibly be is 0, which means that the lowest expected mean squared test error is that variance is the irreducible error. So again, this is showing what the lower bound on the error is. Now let's quickly look at the classification case. So in classification, it doesn't really make sense to have a mean squared error. So instead, we use a misclassification rate. So again, we have n data points. yi is the actual value for the ith data point, and y hat I is the predicted value. And this I is called an indicator function, and it gives the value 1 if the thing inside the brackets is true, and it gives the value 0 if it's not true. So this is just saying if the predicted yi value is not the same as the real y, as the actual yi value, then it will count as 1. And if it is the same, if it doesn't make an error, then it will count as 0. So all this is doing is it's going to count up the number of cases in our data set where that have been misclassified. And it turns out that this is what you can use as one way to measure the accuracy of our data set. So the test error rate would be the average of this. So the best classifier that we can do is called the Bayes classifier. Now we haven't really come across this probability notation yet, although you may have in other subjects. What this is saying is that the Bayes classifier, so this is a conditional probability. It's saying the probability that y is equal to j, so the classification value for y is j, one of the class values. So the probability that y equals j given that the value x is at x0. So it's the conditional probability of the result being j given at that particular value of the data point x0. So we want to choose the j that gives the highest posterior probability or conditional probability. And it turns out if you do that, that's about as good as you can do. And this is called the Bayes classifier. So for a binary classification, if the probability, where there's only two classes, class 1 and class 2, the probability that y equals, so if the probability that y equals j given at x equal to x0 is greater than 0.5, then we choose class 1, otherwise we choose class 2. And this is the best classifier we can do. And we can work out the error on that. It's 1 minus the expected value of the j that gives the maximum posterior probability, and its expectation over our entire data set. That's called the Bayes error rate. That's essentially like that green line that we see in the diagram before. So you might say, well, why don't we use the Bayes classifier all the time? Why do we need to do all this classification with decision trees and all other kinds of methods? Well, unfortunately, it turns out that you can't use the Bayes classifier unless you understand the conditional distribution of y given x at all the different points. And you can't really work that out. So the Bayes classifier, it's a gold standard, but in practice it can't really be worked out. So that's it for this week's lecture. One thing I just wanted to point you to, though, is this last book, so chapter 2 of James Whitten, Hastie and Tibshirani, An Introduction to Statistical Learning with Applications in R. So this is a really nice book that talks about, that can give a really nice introduction to statistical learning. In particular, it talks about the bias variance. So that second part of the lecture is really following what they're talking about. Okay, so I guess I'll see you in class.